Okay, so the setup is standard. I'm not going to go into too much detail about PDMPs because they've already been well explained by the first two talks. So, however, the general setup is we have a target that's given in terms of a potential U. We want to compute expectations. Let's say it's a generic problem. It's very important. Okay, so the general idea is that in high dimensions, classical methods tend to struggle because it's hard to produce large moves that get accepted with high probability. HMC tends to be widely accepted as the state of the art. So if you believe in the scaling limit mantra, then for IID targets at least, then HMC tends to scale like d to the 5/4, which is better than d to the 4/3 for Mala or d squared for random walk metropolis. Obviously, this has to be taken with a grain of salt because as soon as you move away from IID targets, the scaling for most of these algorithms changes drastically. So, however, it's widely accepted that HMC is possibly the most efficient thing out there in the moment. So the question is, what happens beyond the IID scenario? So there have been a lot of papers recently trying to understand how HMC mixes, usually in some form of the smooth convex case for the potential U. So the typical set of assumptions is that you've got strongly log concave target, and the gradient is the gradient of U is globally Lipschitz, and then you've got these two parameters, little and large m, and mixing is usually given in terms of these parameters and often the condition number of the Hessian, which is the ratio of these two. So in some cases, these conditions are allowed to fail. For example, they can fail locally. So around in a small, well, small or large ball around 0. And in that case, you need to kind of replace the global assumption with something that, for example, pulls you towards the origin, like a drift condition or warm start or something like that. And interestingly enough, when the exact dynamics are used, the mixing is independent of dimension, which is kind of what I want to talk about today. So I'm not going to talk about the practical version of HMC, the one you'd be using to do any sampling. I'm going to talk about a PDMP version of HMC, which is known as randomized Hamiltonian Monte Carlo. So we introduced the standard Hamiltonian, which is the sum of the potential U plus Gaussian velocity. We've got a sequence of arrival times of a homogeneous Poisson process with rate lambda. So we call them T1, T2, and so on and so forth. You start from an initial location and velocity x0, v0, and then up until the first arrival time, what you're doing is you're solving exactly the Hamiltonian flow with respect to h. Then at time t1, you can resample the velocity. You can do that either independently, so you sample a fresh copy of standard Gaussian in n dimensions, or you can do it autoregressively using a standard AR1 scheme. So obviously, it seems that it should be better. This actually feeds into the discussion we had in the breakout room. It seems it should be better to do independent refreshments, but we choose to deal with the autoregressive case because of technical reasons. So, so if you take the independent refreshments, then it's not Feller. The process is not Feller in the C0 sense, because you can always jump back to the origin from infinity. Whereas if you take alpha strictly less than 1, so strictly more than 0, which means you have an autoregressive component, then the process does become Feller. Okay, so this process, randomized HMC, has been studied in the past. So in the context of MCMC, it was talked about first by Burabi and Sancerna back in 2017. And it's, as I explained earlier, it is a PDMP. So I'm not going to go through the definition of a PDMP because it's already been introduced. But you can see, for example, here that the deterministic the event rate is independent of location and velocity. So you're having events that are arriving with constant rate, and the jumps are either due to the autoregressive schema explained or just independent refreshments. Okay, so what do we know about RHMC? Burabi and Sancerna proved geometric ergodicity that we're using drift and minorization. It's also studied in the paper by Dolbo et al. From 2015 that Ben mentioned in his talk. So the question, so in Burabi and Sancerna, obviously there is a geometric rate which is not explicit. It's usually hard to get explicit rates using drift and minorization in high dimensions. In many cases, because the minorization condition is hard to scale very well. I think in these PDMPs, it's quite hard. I think Pierre Montmarché have some coupling that may be able to do this efficiently. But in general, it's hard to keep a sharp dependence on the dimension. I guess a notable exception is for Gibbs, for some types of Gibbs samplers, let's say on hierarchical distributions in high dimensions. There it may be possible to get dimension-free rates, but in general, it's quite hard. So that's what I want to talk about. I want to talk about dimension-free rates for RHMC. But before I go on about that, first, let's mention that this is something that previous talks mentioned as well. So all the PDMPs that appear in MCMC, even including RHMC, are non-reversible. And since the seminal paper by Percy Diaconis, Susan Holmes, and Radford Neal, it's almost become folklore that non-reversible processes speed up exploration. Essentially, the idea, at least in the folklore sense, is that if you consider a flat region of space where the density is roughly constant, then detailed balance translates almost to random walk, and therefore this would force diffusive exploration of space. So we're hoping that using momentum, you can go through such regions of space ballistically. So obviously, there's no free lunch. So by starting to look at non-reversible processes, although we have more flexibility, let's say, they're harder to analyze. So the first thing to go, for example, is that for non-reversible processes, geometric ergodicity is no longer equivalent to spectral gap. Obviously, I have to quantify these terms because there may be many things that someone could call geometric ergodicity and many things one should call spectral gap. So in this sentence, I'm talking about geometric ergodicity in the total variation sense. And spectral gap in the L2 sense. Okay, for reversible processes, the two are equivalent. For non-reversible processes, there is an example of a Markov chain that is geometrically ergodic in the TV sense, but doesn't have a spectral gap in L2 in the sense that there's at least one L2 function that doesn't satisfy the standard central limit theorem with root n, because this asymptotic variance is infinite. Okay, so let's go a little bit through how one would prove exponential convergence from a spectral gap for diffusions, and then we'll see how this ties into the rest of my talk. So for diffusions, usually one uses something which I will call spectral gap inequality to distinguish it from a spectral gap, which essentially is an inequality for the Dirichlet form. So you're assuming that the Dirichlet form for the generator is lower bounded by some constant times the variance of the function, at least if you look at functions with zero mean. Okay, now, why is this interesting? Well, if you take the time derivative of the norm of the semigroup, the L2 norm of the semigroup, then you can show that it's exactly equal to the Dirichlet form applied to the semigroup. And then using the spectral gap inequality, so inequality 1, and Grunwald's inequality, you get an inequality of the form 2 for any function with zero mean. Okay, so in fact, for a general Markov process, even non-reversible ones, inequalities 1 and 2 are equivalent. Okay, so let's see how this breaks down if you look at RHMC. So if you write down the generator of RHMC, it's first order, and it's antisymmetric. That's the component A. And the second component comes from the refreshment, and it only affects the velocity component, and it's symmetric. Okay, so the Dirichlet form, when you're looking at the Dirichlet form applied to the same function, then it only depends on the symmetric part, which means that in this particular case, and in fact for any PDMP used in MCMC, any kinetic equation, in fact, if you look at functions that depend only on the location component, then the Dirichlet form becomes 0, which immediately means that there may not be a spectral gap inequality on the Dirichlet form of the form of equation 1, and therefore it means that there may not be an inequality of the form 2 with a non-zero constant. Okay, well, obviously with mu is equal to 0, then that's just the contractivity of the semigroup, so it's not interesting. Okay, so essentially we cannot have something like this. So again, a word of caution, there's usually spectral gap is defined as the distance between the eigenvalue at 0 for continuous time processes and the rest of the spectrum. For Markov chains, it's the distance between the eigenvalue at 1 and the rest of the spectrum. For reversible processes, the two notions are equivalent, but for non-reversible, they are not. So for example, although even for BPS in one dimension, what I explained earlier also is true. So the Dirichlet form is degenerate. You can show, and it has been shown by Joris Birkens in 2019, that it does admit a spectral gap in the classical sense, so that the spectrum is separated from 0 by a positive distance. Okay, obviously you can use this to compute convergence rates, but the approach using the Dirichlet form is usually easier, especially when you have when your target satisfies a Poincare inequality, for a reason that I'll show very soon. Okay, so essentially what we've just seen is that if you look at the norm of the semigroup, then obviously that cannot decay exponentially with a non-zero rate in the form of the equation at the top. So the only question that remains is whether we can relax this inequality by allowing it to hold up to a constant c. That obviously has to be more than 1, because if it's less than 1, then we're back to the original, which we know is impossible. Okay, so now we're asking whether there is a constant c more than 1 and a positive mu, such that an inequality of this form holds. So maybe it's time to pause for a little and think what this would mean. So obviously the constant here being more than 1 means that essentially this inequality cannot tell you anything about mixing, at least at the very first few time instants. So for a very small amount of time, we cannot actually say anything about contractivity because this inequality is trivial. And this is similar to cutoff. So cutoff phenomena in many of algorithms that have been analyzed in the literature, but the difference here is that it's happening in L2. So usually the algorithms where cutoff has been studied, they are reversible, and cutoff has been studied in TV. So if you looked at in L2 for those algorithms, then the inequality with C more than 1 here, it can also be proven to, so in the reversible case, you can always remove the constant and make it equal to 1 using spectral calculus. In fact, you can see the way it's done is very well explained in a paper by Martin Hare, Andrew Stewart, and Sebastian Vollmer from 2014 in also applied probability. So this is kind of a distinct phenomenon for non-reversible processes where you can have this type of cutoff in L2. And also, if you think about why this could be happening, just imagine the situation where for a very small amount of time, after you initialize from a deterministic location, x0, v0, you've got no events. So obviously the probability of this event happening decays exponentially, but condition on this event, there's obviously no mixing, okay? So we can think about the fact that, so this means that for a very short amount of time, the mixing is mostly dependent on the probability of there being no event, okay? So that would be kind of an upper bound on the mixing rate, at least for very, very small amounts of time. Obviously, after 2 or 3, then that's captured by this inequality. Okay, so this type of approach where you're trying to prove such an inequality with a constant more than one is widely known as hypocoercivity. It was coined like that the term was coined by Cedric Villani, and the approach I'm going to show you is based on Villani's approach, which is slightly of a different flavor to the approach taken by Christoph Alain-Durmus and their co-authors, which is more general, but it's based on the approach of the Dolbeau, Moore, and Schmeiser paper. So let's go a bit into more detail. So essentially, the idea goes back to a paper by Neal and Helfer, which in a paper that studied the Fokker-Planck equation for the underdamped Langevin diffusion. So they're looking at the adjoint semigroup acting on densities. And the idea there is to look at a twisted Sobolev inner product. I'll explain in a moment why we have to take this twisted inner product. But the idea is that because you're only pumping noise into the velocity component and not into the location, the only way that the noise is propagated into the location component is through the dynamics. So the only way to capture the mixing in the x dimension in the location component is by trying to look at how the velocity and the location components interact in the same way that hypoellipticity is trying to prove smoothness for all the components, even for the non-degenerate ones, by looking at how the noise propagates from the non-degenerate components to the degenerate ones through the dynamics. Okay, so once you define this type of H1 norm, you have to choose the constant, so it's equivalent to the standard Sobolev norm. Then you look at the time derivative of the norm of the semigroup in this new Sobolev norm. Okay, and the idea is similar, so we will try to look at this time derivative, and then we'll try to force some kind of coercivity, but in this new modified norm. Okay, so this is roughly what I explained earlier for diffusions, but I want to go one step further. So after you do, for standard diffusions, after you differentiate the L2 norm and you get the Dirichlet form, usually for diffusions, it's easy to define some kind of inequality that brings in the Laplacian, and then you can use a Poincare inequality essentially to prove coercivity. So once you put everything together, you'll get an inequality that you can see of the form of the bottom of the page, and then you can apply Grunwald. Now, the issue here is that if you try and do this directly with the L2 norm, you will get the Laplacian, but this will be the Laplacian only in the V dimension, okay? So this is not enough to force coercivity, because if you look at the product measure, then the Poincare inequality that holds also contains this red term that you can see here at the bottom of the page. So you must also have the derivative in the Laplacian in the X component. Obviously, to see why it cannot hold without the red component, just look at a function of X only, where the V derivative will be exactly equal to 0. Obviously, this cannot hold. Okay, so the whole point is we're trying to, although we already have the grad V term, we're trying to make the grad X term appear. So if we look at this twisted Sobolev norm and we take the time derivative, then I've color-coded the terms just to see what's happening. So the blue term is the grad V term. So this will also be present in the standard Sobolev norm, as would the red term. But it's the green term that we have introduced. And in fact, if you take the time derivative and you work through the algebra, a lot of which was actually done for us by Villani in his monograph, so you'll get the grad V term as you would expect from the blue term. You'd get some terms from the red term, but actually the grad X term, which is the one we were missing and we really wanted, is coming from the cross term, from the green term. So you put everything together, you get a quadratic form in grad X and grad V, and then obviously there's some parameters apart from A, B, and C. There's the refreshment rate and so on and so forth, but you can try to optimize a quadratic form to get at least the lower bound on the rate. So again, this mixed term is trying to capture how the component into the location component. Okay, so at the end of the day, you get an inequality of the form at the bottom of the page. So you've got exponential mixing, but it's in the subalef norm. Okay, so the question then is whether could this be true just for functions in the subalef space? So obviously this is a dense subspace, but it's much smaller than L2. So could there be functions in L2 that don't mix exponentially fast? The answer is no. Now, how this is to do this so the way Villani does this is by proving regularization. So obviously we've got we've got an inequality. We can bound L2 norm by the subalef norm using the Poincare inequality. It's the opposite direction that's quite tough, and obviously it's impossible. But what you can prove is that after a small time interval, if you look at the subalef norm of any L2 function propagated by the semigroup, then you can bound that by the L2 norm of the function times some singular constant that blows up at time 0. Now, Villani did this for the Fokker-Planck equation, where you got continuous noise pumping into the system. I'm not saying it's easy, it's hard, but in our case, where the jumps arrive at the arrival times of Poisson process, it's even harder because you have to essentially discount the possibility of there being no jumps or maybe 1 or 2 jumps, and then you have to look at the sub-Markov semigroup that is capturing what happens after at least 2 jumps. Anyway, so we opted for a different approach. So in fact, for RHMC, although it's non-reversible, if you take the time reversal, it looks very similar. It's just the same process, but the asymmetric part has picked up a minus sign. And what you can do is you can actually prove pretty much the exact same contraction for the time reversal. Now you can combine then the semigroup with its adjoint at, you can compose them at time t. You can get this self-adjoint operator Q. And in fact, what we've just proven is that in this subalef norm, at least we got this type of contraction for this self-adjoint operator Q. So P star TPT. Obviously, this is self-adjoint in the L2 sense, not in the subalef sense. But we will see in a second how you can leverage that to prove contraction for all of L2. So you put everything together, you can iterate inequality 4, and you can prove now a contraction in L2 at least for functions in the subalef space or for Lipschitz functions, and you get a bound of this form 5. Now the interesting part about this is that because Q is self-adjoint, there's a result that's explained very nicely in the paper, again by Martin Herrer, Andrew Stewart, and Sebastian Vollmer in 2014. It's also a trick that's been used by Olivier in his paper for metrics for Markov chains, but the explanation there is a little bit more quick, so it's not as clear. Anyway, the idea is that if you have such an inequality with some constant for a specific function f, then you can remove the constant and replace it by the variant for the specific function f. And since we've got this inequality on a dense subspace of L2, then we can actually extend it to the whole of L2 and get a spectral gap. So I explained this in much more detail because the last time I gave this talk in January, this is the part that I got the most questions about. So I thought perhaps this is something I should explain in more detail. Okay, so in fact, using this idea of like mixing the metric up, you can even prove contraction in Wasserstein, and you don't have to do any fancy couplings. You just do you just take 2 copies of RHMC and you couple them synchronously, and you can show that it's contracting globally. And this is the rate that we get for a specific refreshment rate that we tune according to the condition number. So in principle, compared to other existing results for HMC, we tend to get a slightly better dependence on the Hessian, on the condition number. And obviously there's more recent results as well. Obviously there's a paper by Christoph and Alain Dermus, and there's more recent papers in the past couple of years. Thank you very much.
Thanks,
I
George.
I thought everyone was gone.
No, we are here. It's just
Okay.
it took a while to hear you back, but most of the time we could hear you clearly. It's just a few times it was skipping a little bit. But so, uh, any questions to George?
Yes, so it's Pierre Marché. I had a question at the end. So you explained the H1 hypocoercivity, and then at the end you mentioned the Wasserstein coupling. And so I looked at your paper, so I saw these two parts, and so the Wasserstein is in a convex case, but apart from that, I mean, in both cases, at the end, you have the same argument that gives you a rate in L2. So, for instance, in the convex smooth case, uh, are your rates different when you obtain them from H1 or for Wasserstein? Is there a difference, or is the Wasserstein just I'd say the results that you get in L2 from the Wasserstein coupling, is it strictly weaker than the H1, or is there some distinct things?
To be honest, I don't really remember. I think the rates were the same, or at least were this had the same. Depend. Maybe Daniel remembers, but I
Yeah,
think
they were the same, exactly the same.
Okay.
Yeah, somehow we got the exact same rates in those two cases. It's possible that you could push the argument in using the Sobolev norm a little bit further by not by using a Poincare instead of uh, just strong convexity, but we didn't pursue that in the paper.
Yes, because here you don't use the Poincare inequality. You really have a contraction of something where there is only the norm of the gradient and there is no L2 part in the.
can you repeat that? Can
You
you
know,
repeat that?
in Villani's calculations,
Yeah.
you don't have you don't have a closed inequality only by differentiating something which is the L2 norm of some twisted gradient. You also have to put the L2 norm to have some extra derivative in V.
Okay, okay.
So you are not doing that. If I understood correctly, you just have a strict contraction only with a twisted gradient, and so you don't use the Poincare inequality. And then, so is it that? Is it what you're doing?
Well, so we're using explicitly the lower bound on the
Asian.
eigenvalues of the Hessian
Yeah.
when we're optimizing the quadratic form. We're using the lower bound and the upper bound explicitly in the optimization.
Okay. And then, okay, so I think it's natural that you get the same rates because you have results either from Olivier or from a Kuwada that tells you that if you have a contraction in W2, then it's equivalent to have a contraction of the gradient along the semi-group. And so if you just integrate one, you get, well, I mean, there is some equivalence of these two things. So
You mean from H1 to L2?
no, I meant from Wasserstein. So if you have
Oh yeah, 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 yeah. But
Markov
in
semi-group
the
that contracts W2, the W2 distance, then you have a gradient of PT, the square of the norm of PTF, which is bounded by exactly the same contraction rate times PT of the square the norm of the gradient. And so if you integrate this subcommutation between semi-group and gradient, you exactly get a
yeah, yeah,
decay
yeah.
in Sobolev norm. And so, okay, so it makes sense for me that you get the same rate since a posteriori you could get one rate from the other you could get the mean of your two rates.
But so part of the argument that I explained, so I gave a different reference, but I also mentioned, so you mentioned the paper by Olivier. Yeah, it's essentially the same idea. It's just that I gave it also a different reference because I had some discussions and some people didn't really like the argument in Olivier. Although it's correct, it's not very well written. So actually it was Gabriel Stolze was one of those people who didn't like the argument in Olivier. So I also gave a different reference. But yes, that's the idea. That's the idea.
Okay, thank you.